Okay, so we are going to start today's discussion by talking about something that we started last time, which is to understand liquid vapor phase diagram in a two-component system. When you have a component A and a component B, we have already seen how it looks like in a one-component system. We looked at the water phase diagram and we saw it was very well. We studied it in great detail, but the question is, how does it look for a two-component system, A plus B? So our starting point for this one, also this is going to be our plan of action. We are going to consider the free energy for the vapor as function of xb, the mole fraction of B. We are going to compare the free, we are going to look at the free energy of liquid as function of mole fraction of B. And whenever GV is less than GL, we know vapor is going to exist. Whenever GL is less than GV, we know liquid is going to exist, right? This is the direction of spontaneous change. So if, and I know my L and, no, my L and B are okay. It's not too bad, but you can ask me in chat if there's a question. So this is what we want to do. In order to do that, we will start with a range of temperatures. We will start with a very high temperature. Very high T is equal to T1, okay? At an extremely high temperature, G is equal to H minus Ts will be predominantly given by minus Ts, right? Because temperature is so high that entropy dominates. The enthalpy becomes relatively insignificant. So at a very high temperature, furthermore, what can we say about entropy of vapor with respect to entropy of liquid? We expect that entropy of vapor will be much more than entropy of liquid. It's just so easy to be disordered if you're a vapor as compared to liquid, right? What does this mean? This means that minus Ts vapor is going to be less than minus TSL, right? You're multiplying by a negative number both sides. Therefore, G vapor is going to be less than G liquid. So this makes sense at a very high temperature. And let's draw. So we will be doing a bunch of math on the top, and here we will be drawing pictures to show how it looks like. So we are talking about how things, and I'm going to draw a bit small because otherwise you will have to swap between pages and it becomes even more confusing. So so we are talking about free energy of the vapor at a very high temperature, T is equal to T1. So at the very high temperature, we have just shown that GV is going to be smaller than G liquid. How is either of these curves going to look like? Well, we saw for a solution, it drops down with a slope of minus infinity, catches up with a slope of plus infinity, something like this. And I don't really care whether it's symmetric or asymmetric at the other end. Those things depend on the chemical potential of pure A and pure B. Some curve like this, which is my G vapor, and in blue, I will be drawing my G liquid, or not blue, in red, I will be drawing my G liquid, okay? So this is true because we know G vapor is less than G liquid at a very high temperature. Now let's go to a slightly lower temperature and see what happens. So now we are interested in a temperature T is equal to T2, which is smaller than T1. So in order to do this, in order to understand how will these free energy curves move when you decrease the temperature, we look at our favorite, hopefully, thermodynamic relation, dG is equal to V dP minus S dt. Therefore, partial G by partial T at constant P is equal to minus S, right? Why is this relation very important? Because this tells us that delta G, the change in free energy, corresponding to a change in temperature delta T is going to be given by this relation. We can do this for vapor. We can say delta G for vapor is going to be minus SV multiplied by delta T. And we can say delta G for liquid is going to be minus SL multiplied by delta T. So we are talking about a decrease in temperature, right? Decrease in temperature means delta T is negative, right? Multiplied by SV, so multiplied by minus SV or multiplied by minus SL. So you're taking something negative and multiplying it by something else which is negative. This is a simple fact which really makes all of this. If this point is the most important point for understanding how this phase diagram looks. When you go back and look at your notes or the video, make sure you understand this point. If you get this one, what I'm drawing next is all really easy. But if you don't get this one, it will become confusing. So delta T, I didn't mean to erase it. Delta T is negative and entropy is always positive, right? So minus entropy is also negative. So the product of two negative things is going to be, their product is positive. And this applies to both GL and to GV. However, which one is going to be more positive, delta GL or delta GS? Anyone wants to put something in chat? Delta T is negative. Delta T is negative because you brought the temperature down. What do you mean by VL? I don't know what you mean by VL here. For either system, you are thinking about T1, about T2, which is lower than T1. It's just negative. So which one? So we know that delta GL is positive and delta GV is positive. Now, since we just showed that SV is more than SL, therefore delta GV is going to be more than delta GL and both will be positive. This is what we just showed. This is what I meant by the important part over here, all of this. This is super important that you get this right. So we used our partial G by partial T at constant pressure is equal to minus S. And then we said that, well, S is always positive. So for a decrease in temperature must correspond to free energy increasing. When you're getting a decrease in T, what are you decreasing it from? From T1. We went from T1 to T2. Decrease from T1 to T2. Okay? So we went down from T1 to T2. So this is our thermometer. T1, T2. This is our thermometer. And somewhere over here it's absolute zero. And this is, I don't know, nuclear fusion temperature. Some very high temperature. Okay, so we are going down from T1 to T2 and so on and so forth. So both of these curves are going to move up. However, the vapor curve is going to move up a lot with respect to the liquid curve. So relative to this on the left, the liquid one will look something like it moved like this. It moved up slightly, our G liquid. The vapor curve will, however, look like it moved a lot. It will look like it almost caught up with the G liquid. Now we go to a third temperature, T3. We go to T is equal to T3, which is smaller than T2 and smaller than T1. So we decrease the temperature even further. What's this going to look like? If you do this even further, you can again draw this. Now, what's going to happen is that G liquid will continue to move. So I will have to, and I'm just going to write it down here because otherwise I will run out of space. Moves both curves move up. G liquid will continue to move up, but the G vapor will now have moved up so much that it's going to intersect it at some point. And that's where things start to get interesting. So now, and we are going to look at this in detail in a moment as to what exactly happens at this intersection, but I want to write down one final temperature or two more temperatures, and then we will come and look back at the intersection more carefully. If you move it a temperature further, so let's say you go to T is equal to T4, which is even smaller than T3, you decrease the temperature even further, these curves will continue to move up, but now again, the black curve will keep moving more and more. The red curve, the liquid curve, will move. So this is liquid, and this over here is vapor. The liquid curve will move up, the black curve will also move up, but the black curve will once again move up more with respect to liquid. So now it's going to look something like this. You will have the liquid, which goes like this, and the vapor, since it has moved up, will come and intersect at some point which has moved to the right. So if you look at this intersection point over here, the intersection point has moved to the right. And I'm going to do one more temperature, and then we will look at this intersection behavior more carefully. So finally, and again, I want to emphasize that both have moved up over here. So for example, if you want to draw, yeah, just keep in mind that these curves on in the right one are not, these curves are not parallel to these curves. I'm trying to indicate that they have moved up. As here, it was obvious that they have moved up, but then I ran out of space, so I can't really do that over here. So finally, at a temperature which is extremely low, T is equal to T5, which is smaller than T4, which is smaller than T3, which is smaller than T2, which is smaller than T1. What will happen is that the liquid curve, sorry, the vapor curve would have moved up so much higher that it will stop intersecting the liquid curve. So now the vapor curve will look like this, and the liquid curve will look something like this. So it's very much similar to the first T is equal to T1, but now you have G vapor sitting above G liquid. So at a very low temperature, liquid will always be stable. So we can draw all of this in a phase diagram. How do we do that? This over here is temperature. This over here is mole fraction. Let's start with our very, very high temperature T1. At T is equal to T1, we know vapor is stable all through for all values of the mole fraction. It's only vapor, right? So it's going to be vapor, 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 vapor. Okay? Now, when you decrease the temperature and you come to T is equal to T2, it is still vapor, 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 right? Now you come to T is equal to T3 and something interesting happens. There is a point to the left of this point until which liquid dominates, and there is a point, and to the right of this point, vapor dominates, right? So you know that for very left over here, you are going to have liquid, and very right over here, you are again going to have vapor. What happens is that there is a middle region in which you have both liquid and vapor. And how exactly this middle region is formed, we will do just in a bit. For now, you have to take my word. You can see clearly from this plot. Let's zoom in. That ordinarily you would have thought that to the left of this black circle that I just drew, everything to the left would be liquid and everything to the right would be vapor. So normally you would have imagined that, okay, everything to the left is going to be liquid and everything to the right is going to vapor, right? That's the obvious conclusion, right? Because you see that the red curve is below the black curve to the left of this, and the black curve is below the red curve to the right of this. In practice, in reality, that doesn't happen. You end up with something that looks like this. The liquid dominates only in this part, and the vapor dominates in this part, and the middle part is coexistence, liquid plus vapor. And again, we will get to why the coexistence happens after we finish this phase diagram on the next slide. So you have liquid, you have vapor on the far right, but in the middle, you have L plus V coexisting together. Same thing at T is equal to T4. It's the similar physics, but the only difference now is that the liquid exists for a bigger region. It pushes more into the vapor. So you have liquid, liquid. To the far right, you have vapor, vapor. And in the middle, you are going to have a bigger liquid plus vapor region, which has also started to appear more from the right. And as you finally go down to T5, everything has become liquid. So we can take this and mark our phase boundaries in this. This is a very discrete grids, right? I have only drawn 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 grid points. So it's kind of discrete, but if you did it carefully, you can see a pattern that starts to emerge. You have a liquid plus vapor region that looks something like this. To its left and below, you have liquid. To its top and right, you have vapor. And this is your two-phase liquid vapor phase diagram for a two-component system. And this is how it comes. The thing that I have skipped so far is, why do you have liquid plus vapor coexisting in this region? Why don't you just have liquid, all of it suddenly changing to vapor? We will get to that just in a moment. Assuming that you buy that argument, that I'm going to tell you that in a moment, any questions about any of this before I move to the next page? No questions? Okay. So let's focus on this one on next page. What's really going on over here? So yeah, and before I do that, the key idea here was at very, very high temperature, liquid free energy is always higher than vapor free energy because entropy dominates, because G is equal to minus Ts approximately. However, using this identity, which is true for everything, we know that the free energy is going to increase when the temperature change is negative. However, the proportionality constant with respect to temperature is minus times entropy. And we know that vapor has higher entropy than liquid. So using this basic math, we came up with a very physical argument that the free energy for vapor curve, vapor moves up, G vapor moved up a lot, G liquid moves a little. And that's how at some point the G vapor comes and intersects TG liquid, and then the intersection point at which it first intersects keeps moving to the right as you increasing the temperature. And finally, at some temperature, there is no intersection and you have liquid everywhere. So let's look at this middle one on the next page. When they intersect, what exactly happens? So it's so important that let's draw it in a very, very big plot. Okay, so here I have my XB going from 0 to 1, and I'm talking about G, which will be G vapor and G liquid. So, and I'm talking about any one intersection. So what colors am I using? I'm using G liquid in red. So this is my G liquid, and I have a G vapor. I don't know where it went, sorry. So I have a G liquid in red, and I have a G vapor that looks like this. So let's mark them. This is our G liquid, and this is our G vapor. And we are at some temperature, let's say T is equal to T3, where they intersect at a point. Now you might say, why do they intersect only at one point? Why don't they intersect at more than one point? Of course, they very well could. Your phase diagram starts to look more and more complicated. It will look like you can get all sorts of shapes out of phase diagrams, like depending on how the things intersect with each other. Furthermore, you might not have only two phases in the phase diagram. You might have a third phase free energy existing like this, right? And then it becomes even more complicated. Or you might have a fourth phase that comes and goes something like this. And then you really have to be very, very careful. So, but if you get the concept behind the two correct, going to 3 or 4 phases, it's just being meticulous about your bookkeeping. It's conceptually not harder. So the point I made here is that if you are at a composition in between, so there is a middle range of composition at which the system exists as liquid plus vapor in a two-phase form. To the left of it, it's going to be liquid. To the right of it, it's going to be vapor. Why does this two-phase existence happen? The reason it happens is that if you draw a line here, which is called, let me first draw the line and then I'll explain to you what exactly it is. So it's a line that touches this curve and touches the black one. I gotta do, this is why I was, let's see if I can draw it right. It's supposed to be a straight line, okay? It's a better way of drawing it. So this is a straight line, which is tangent to red curve at XL, okay? So some XL, and tangent to black curve at XV, okay? There can be only one such line which is tangent to both of them at any point. Why is that the case? Because if you just think about the red curve and you place for the red curve at any point, you can draw a tangent, right? You can draw a tangent that will look like this. At this point, you can draw a tangent which will, you can keep drawing lots and lots of tangents. There is only one unique tangent which touches both of them, which there is only one such unique line which can be tangent to both curves. And figuring out coexistence of phases really amounts to solving for the equation of this line and where does it become tangent. So it becomes tangent to the liquid curve at composition XL. This, and again, we are talking about composition of component B in the liquid phase, okay? So actually a better word for this might be, a better letter for this might be 1, otherwise it will confuse you. Let's call this composition X1, and this is mole fraction of the B phase. And over here, it is making a tangent at some composition X2. So my claim is that in this middle region, in between the 2 points where you found the tangent, you are going to have liquid plus vapor coexisting. In this region, you are going to have liquid plus vapor, and to the right of it, you are again going to have vapor. So the vapor starts from here. This is all vapor. In the middle, you are going to have liquid and vapor both. Why is that the case? That is actually quite easy to understand, because what would we have normally thought? We would have thought, well, all until this point, the red curve is below the black curve, right? So we started from some composition 0, and what do we see? The red curve here is below the black curve. We come to some other composition, red curve is again below the black curve. We come to this composition, red curve is again below the black curve. And we would think that ordinarily, that until this point, red curve is below the black curve, so you should have only liquid. And then we would say, well, and at this point now, the black curve is below the red curve, so you should have only vapor. However, what happens is that if you consider this point, for example, or let's look at this one over here. And I will have to zoom in. This is why it's a tricky construction to draw. I have already posted, and I will post some more material on this where this is done with very carefully drawn curves that people have taken a lot of time to draw. So you can go back and revisit that concept, but just try to get the basic gist over here. And let's say you have a black curve, okay? So this is zoomed in. And we drew our common tangents that look something like this, okay? So this point over here could exist as only liquid, or it could exist as a combination of a liquid and of a vapor in some ratio. And if it existed in that ratio, it would have a free energy G2, which is lower than the free energy G1 if it existed only on the red curve. So G1 is equal to pure liquid. G2 is equal to some combination of liquid, A multiplied by G liquid over here, plus 1 minus A, because things have to add up to 1, multiplied by G vapor over here. And as you can see, G2 is always lower than G1. Therefore, it's in the interest of the system, if it lies between two common tangent points, to drop down and exist as a two-phase region. This is a subtle argument. I think you all should be able to understand it, but if not, I can post a second video on it, and I will post extra material. But this thing that I just drew is really fundamental to thermodynamics. It is called the common tangent construction. And this middle region is where you will have liquid and vapor coexistence. Now, I would like one of you to help me answer or understand as to why did I draw the tangent? What is special about the tangent? Why did I equate the slopes? So what is special about this line? What is special about this line? That it says that partial GL by partial XB is equal to partial GL by partial GV by partial XP, right? That is the common tangent construction if you really write it down mathematically. Why did I go for this property? Any ideas? And this is at constant temperature pressure. And it's a it's a two component system. Chemical potential, exactly. Absolutely correct, Molly. This is the beauty of chemical potential. If we want liquid and vapor to coexist, their chemical potential must be same. What is chemical potential? This is why I went into chemical potential again last time, because if you were confused about chemical potential last time, this class would have been a disaster, or maybe even more of a disaster. Hopefully it's not too bad of a disaster. This is mu L on the left, and this on the right is mu vapor. And in order for two phases to coexist, the chemical potential for any species across them in both phases has to be same. You can do the same thing for XA, but XA is equal to 1 minus XB. So it becomes simple. That's why we do this common tangent construction. So the person who came up with this common tangent construction was Maxwell, the physicist. who has Maxwell's laws and Maxwell's equations and all those things. He came up with this, and this is how we explain our two-phase existence region. Okay, any questions? So another way of looking at it, let me draw a better phase diagram now that we have done this. And if you understand today's discussion, then any complicated phase diagram that you come across is the same idea, drawing free energies, trying to put in common tangents, looking at coexistence regions. It gets a bit more complicated if you have inflection points in the middle. It leads to something called miscibility gap and spinal decomposition. It can get richer, but the key idea is what we just drove over here. Drew over here. Look at the common tangent, and that's the region where it's energetically favorable to drop down from a single phase region like this one in red to a coexistence of two phases, which is below on blue. And you can see because the line is below it, right? So this point is given, this AGL plus 1 minus AGV is the equation of this line over here. And it's better to drop off to that because your free energy goes down. So our liquid vapor phase diagram that we drew with grid points over here, we can draw more generally now. It's going to look like temperature, composition. And I have it downward sloping towards right. It could have been something like this. There is nothing special about it. It could have looked something like this. It could have even been flat. So that really depends on how pure A compares with pure B. But without loss of generality, we would just take one of them. So on the very top, you have liquid. Sorry, on the very top, you have vapor. On the bottom, you have liquid. And here you have liquid plus vapor. And the point being that at any temperature, you are going to have liquid. And if you go far to the right, you're going to have vapor. But in the middle, it's better to exist as a combination of liquid and vapor. Similarly, at this temperature, you can start here, you can go over here, and this is going to be liquid plus vapor. This line has a name. This is called the tie line. It ties the both phases together. A natural question to ask now is, at a given point here, this green point, one moment. At this point O, we just said that the system is going to exist as liquid and vapor both together. But how much? What fraction is liquid and what fraction is vapor? How do we answer that? That's useful, right? Because that tells you how much liquid and how much vapor will you have. If you look at the phase diagram, if you could quantify that, that would be a really super powerful phase diagram because you can directly read out. So far, we have been saying, oh, both liquid and vapor will coexist. But so let's give these things name. Let's say more than just fraction, we want to calculate at point O how many moles of liquid, let's call it as N subscript L, and how many moles of vapor, N subscript V. Let's look at some sample points. Let's look at point number A and well, A and B are bad notation because our components are called A and B. Let's look at point number 1 and point number 5, okay? So point 1 in this picture, what will be the value of N liquid and what will be the value of N vapor? How much will be N liquid? Any ideas? At point 1, what will be, and okay, one more thing, the total number of moles is N. Total number of moles that is fixed, right? We are just changing composition. So at point 1, what will be NL? What will be N liquid? I'm waiting. I need help.
Would it be all liquid?
Cool. So what is our number for it? Small n, right? So it's all liquid. Exactly correct. So it's just going to be N. Who answered that?
Jared.
Oh, cool. I got Jared. Now you have to help me, Jared. And what's going to be N vapor then?
0.
Perfect. Let's go to point 5. Can you tell me what will happen there?
The opposite.
Opposite, 0 and N. Thanks, Jared. Perfect. So we know the endpoints, how they will look like. We want to figure out how it looks in the middle. So as you move from 1 to 5, you know the number of moles of liquid are going to go down and the number of moles of vapor are going to go up. It would be wonderful if you could write down an expression that tells us precisely how they will go up and how they will go down. I'm going to write down the expression first, and then we will go into the proof, because sometimes in thermodynamics, like remember your Gibbs phase rule, F is equal to C minus P plus 2, proof was a bit hairy, it was a bit scary, hairy, whatever you want to call it. It was a bit complicated. Rule itself is simple to remember, and it's also easy to see what the rule is saying. The proof can be a bit complicated. So I'm going to write down the relation that tells us NL and NV along any point in the tie line, and then I will do the proof. So to do this, we will measure. So once you have a phase diagram and someone asks you, tell me how many moles of liquid are there, how many moles of vapor are there, and I can promise you in your next homework or your midterm, I'm going to show you a complicated phase diagram. You'll be like, we haven't done phase diagrams like this, but I will ask you to calculate this thing. And there you will have to focus on how to generalize these concepts. There won't be anything complicated. This can apply to apps. Yeah, you will see what I mean. So let's understand this carefully. So let's call this length as L liquid. Okay, so we are in the phase diagram. We know which is our tie line. We know which is the, so the question is that, let's say this line was not given to you. You were just given a point O, and someone asks you, what is the number of moles of liquid and what is the number of moles of vapor? So what you will do, your next step would be to draw a tie line. And the reason I say that this can work even in complicated phase diagrams is because you could have a whole bunch of phases existing over here doing funky stuff. Doesn't matter, you don't care about any of that. All you care about is this two-phase coexistence region. So you draw a tie line that connects you to the nearest point on the liquid, which is point 1, and to the nearest point on the vapor, which is point 5. I don't know why I call it 1 and 5. I thought I would be drawing lots of points in the middle, but that's okay. And then you measure this length. This length I am calling as L liquid. And then you measure this length. This length I am calling as L vapor. Okay, so you measure the distance from the nearest liquid point, distance from nearest liquid along tie line, and from nearest vapor along tie line. So the relation that I am introducing next is called Lever rule. Lever rule says that the number of moles of liquid multiplied by this length from the nearest liquid point is going to be equal to the number of moles of the vapor multiplied by the distance from the vapor point. And you can see why this makes sense. At point 1, what is LL? The distance from the nearest liquid is 0, correct? At point 5, what is LV? It is 0. So if you go to point 1 and use this relation, you are getting NL multiplied by 0 is equal to NV multiplied by LV. LV is non-zero for sure. We know it is some length at point 1, so this is non-zero. But if NL multiplied by 0 gives you NV multiplied by LV, this means that NV is equal to 0. And this is what we had over here. So it follows our common sense that Jared told us about. It follows that. Similarly, over here, you have NL, LL is equal to NV multiplied by LV. At this point 5, LV is 0. Therefore, NL must be 0. And that's what we wrote down over here. In the middle, you can see why it makes sense. In the middle, you are saying that as another way of thinking about is that NL by NV is equal to LV by LL. Okay, L capital L, small l subscript capital L. So as you move along this line, what happens to LV? As you move along tie line, LL increases, right? Because your distance, and you could move to the left, you could move to the right. I'm talking about moving to the right. As you move along the tie line to the right direction over here, your LL increases. You're moving further and further from this liquid point 1. Your LV decreases because you are getting closer and closer to the vapor point 5. Therefore, LV by LL also decreases. The numerator is decreasing, the denominator is increasing. Therefore, NL by NV decreases, right? So the number of moles of the liquid relative to the number of moles of the vapor decreases, which makes sense because here we started with all at the left, this ratio was infinity, right? And L was N and N vapor was 0. And as you go to the right to the 0.5, this ratio becomes 0. And that's what this Liver rule captures. It's very generic. It applies to phase diagrams in as complicated positions as you can imagine, as complicated phase diagrams as you can imagine, it still applies. It's only for two-phase coexistence though. If you have three-phase coexistence, you have to be careful. However, we are thinking about binary compositions. When you go, so the tie line becomes complicated in three-component phase diagrams. And I have three-component phase diagrams are complicated. There you don't draw things like this. Three-component phase diagrams look something like this, where this corresponds to XA is equal to 1, XB is equal to 1, XC is equal to 0, XA is equal to 1, XB is equal to 0, XC is equal to 1, XA is equal to 0, XB is equal to, well, not 1, you know what I mean, half. And this, such a triangle is called a Gibbs triangle. This is something we have not done in this class because it is messy. It's really complicated. Drawing tie lines in a Gibbs triangle is way more complicated than what you just did. And that's where we have to worry about three-phase regions. In our simple phase diagram, we mostly get away with two-phase regions. Therefore, this Liver rule and this tie line is quite useful. So this is advanced. It's something we are not considering in this class because we really don't have time for it. So let me finish today's class with Liver rule and proof of the Liver rule. And then when we meet after Thanksgiving, we will start with equilibrium constants, chemical equilibrium constants. that will be maybe one class, then one class on electrochemistry, and then we are just going to do, so we have maybe 2 or 3 classes after this. We will be doing classes after that, but it will be only revision. I will be going over all the full semester with you and making sure everything is clear. And I will probably send out another poll asking you to write down topics that are not clear to you. So I have a sense of what is to be covered. So let's do the proof of this. So in order to prove this, let me draw the phase diagram again. I can draw it sloping like this. And I have a curve. This is the point O that I'm thinking about. This is XB. This is temperature. And this is my vapor. This is my liquid. I have deliberately flipped the orientation. It will force you to think just a little bit, and I think that will be useful for understanding. So now this is my liquid, this is my length vapor, right? The distance from the nearest vapor point, while this over here is my length liquid. And let's call this one as X1, and let's call this one as X2. That mole fraction of B at both these points, where the tie line touches the vapor for the first time, that is X1, and where the tie line touches the liquid for the first time, that is X2. So the way this proof will work is that at point O, we will calculate number of B molecules or B moles, number of B moles in 2 different ways, and then equate both of them. So first, so by the way, today's class is going to run maybe 3-4 minutes longer. If you have to leave, I understand. And the video will be there. Instead of posting a separate video, I'm just going to keep continuing. It will be done by 9:55. It won't be later than that for sure. It's just a bit. I don't want to leave this for after the Thanksgiving break. So at point O, the total number of B molecules will be given by, let's say the mole fraction over here is XB at this point. So this thing is equal to the total number of moles in the system N multiplied by the mole fraction of B, right? Nothing profound about it. If you have total number of moles N and you know mole fraction of B, then the number of moles of B is going to be N multiplied by XB. This in turn is given by number of moles of vapor plus number of moles of liquid multiplied by XB, which is NVXB plus NLXB, right? So this, what are we talking about? We are talking about number of moles of B at point O. So this is our equation number 1. Let's do it in a second way and then equate both. For the second way, we have to think about number of moles of B in vapor phase. How much is that? And we have to think about number of moles of B in liquid phase. And if we can write down both of these and sum it together, then we get first way of thinking. We are calculating number of moles of B in 2 ways. First way is to just say that if the total number of moles is N and the mole fraction of B is XB, then it is NV plus NL multiplied by XB, N multiplied by XB. The second way, we think about number of moles of B in the vapor phase at this point and number of moles of B in the liquid phase at that same point. So how do we get the number of moles of B in vapor phase? That is going to be the number of moles of vapor multiplied by this concentration X1, the mole fraction X1, because we do know one thing. We are thinking about, so this is the point which is subtle. The second way is more subtle than the first one, because here we are assuming that the system is going to exist. We are using our common tangent property. We know that it will exist as a combination of vapor with mole fraction X1 and liquid with mole fraction x2. We know this. So therefore, the number of moles of B in vapor phase is NVX1, and number of moles of B in liquid phase is NLX2. And now we can sum it together. Therefore, number of moles of B at point O is equal to NVX1 plus NLX2. So we have just calculated the number of moles of B in a second way. And now we can equate 1 with 2 because both are giving us the same thing, the number of moles of B. We get NVXB plus NLXB is equal to NVX1 plus NLX2. Therefore, NV XB minus X1 is equal to NL X2 minus XB. But XB minus X1 is exactly our LL, right? Therefore, NV LL is equal to NL multiplied by X2 minus XB. X2 minus XB is exactly LV, and that's our Lever rule. NLLL is equal to NV. No, oh, sorry. This is the vapor one. So XB minus X1. XB minus X1 is equal to LV, as I just marked over here. So and this is our Lever rule. So this part is confusing. The second part is confusing, which is where students get tripped. I recommend to go through this, then shut your notes and try to derive it on your own. And if you can do it on your own, remember, you have to think about the number of mole fractions of B at point O in two different ways. One is to just consider the total number of moles of the system and multiply it with the mole fraction. And the other is to realize that at this point, you have a combination of two phases, vapor and liquid. And you know exactly vapor with what composition. You know it is a vapor with composition given by X1 and liquid with composition given by X2. By composition, I mean composition of B. And you can use both of these to get the Lever rule. So in the homework that you will have after Thanksgiving, I will have some practical problems using Lever rule. If the proof confuses you, that's okay, it doesn't matter. The more important thing is that you are capable of using the Lever rule in practical problems. So the next homework will have 1 or 2 problems on this. Otherwise, I will be having office hour today, 11 till 11:45. And I learned there is no class on Wednesday, which made me very sad, but well, such is life. I will see you next Monday, apart from that. And if I haven't received your midterm, I will let you know, so don't freak out. If I don't see it, I will talk to you separately. Okay. Happy Thanksgiving.